Welcome to the series of screencast presentations on the analysis of kinetic rate data. This is Michael Hill, formerly of Unilever Research and Development and currently at Columbia University. If a chemical reaction is to be properly scaled up, it is essential to have a kinetic model for that reaction, such as the typical models you see here. Of course, it's also necessary to have values for all the parameters in your model. A model with parameters can generally be constructed by analyzing kinetic data obtained in the laboratory. There are multiple ways of doing this, and in this series of videos, we will discuss some of those ways. The usual way to obtain kinetic data is to conduct a reaction in an isothermal batch reactor. There are various advantages to this configuration. For example, the setup is generally simple, and you can obtain lots of data in one continuous experiment over time. On the other hand, the analysis of data is straightforward only if the volume of the reacting mixture is constant, which is usually the case, but not always. Also, the reactor contents may not be truly isothermal, especially if you are controlling the temperature with a simple constant temperature bath. But as we shall see, the biggest disadvantage is that this configuration does not allow you to directly measure the thing you need, the rate of the chemical reaction. In subsequent videos, I will discuss alternative approaches, but isothermal batch reactors are used most often for obtaining kinetic data, especially by chemists. As the reaction proceeds, sometimes you can measure the concentration of reactant or product in situ in real time, perhaps with a fiber optic probe leading to a spectrophotometer, such as an FTIR, or perhaps with an electrochemical probe leading to a device similar to a pH meter. If you can't take measurements in situ, you will need to take samples, quench them to stop the reaction from proceeding further until you can take measurements, and then measure a concentration offline with something like an HPLC or a GC mass spec. This can be incredibly time-consuming, so it is better to find a way to measure a concentration in situ if you can. Eventually, you will end up with concentration data at various points in time. So how do you reduce data like this to a kinetic rate model? We start with a generic mole balance for species A for any chemical reactor. This equation is stating that the net change in moles of A per time in the reactor is equal to the flow rate of A into the reactor minus the flow rate of A out of the reactor plus the change in moles of A due to the reaction. Here, N sub A is the number of moles of A present, F sub A naught is the flow rate of A into the reactor during the reaction in moles per time, F sub A is the flow rate of A out of the reactor during the reaction in moles per time, and R sub A is the rate of the reaction, specifically the rate of appearance of species A in moles per volume per time. The rate of the reaction needs to be multiplied by a differential volume element dV and then integrated over the entire volume of the reactor, which is V. This mole balance is sufficiently general to be applied to various reactor configurations. But for a batch reactor, the two flow terms are zero. In addition, if we assume perfect mixing, the rate of the reaction is the same in all differential volume elements, so it can come out of the integral over the volume. Of course, the integral of the differential volume dV is the total reactor volume V. We can solve this expression for the rate of the reaction, which will change as the reaction proceeds. We can also express the rate of the reaction in terms of the concentration of species A, the moles of A per volume. If the volume of the reacting mixture is constant, as it usually is, this simplifies the result. The rate of appearance of species A is equal to the time derivative of the concentration of species A. If this time derivative is negative, A is disappearing. And if the time derivative is positive, A is appearing. Note that this is not the definition of the rate of the reaction. It is a consequence of the simplifications we have made to our mole balance, and it will not be true in other reactor configurations. But as this equation shows, to get the rate of the reaction at any given time from our batch reactor experiment, we need the time derivative of the concentration of A, dCA dt. Unfortunately, we aren't measuring the time derivative. We're measuring the concentration of A. So what can we do? There are two basic approaches. One way is to use the concentration data to estimate the value of the time derivative at various points in time. This is referred to as a differential analysis. The other approach is to assume a relationship between the rate of reaction and the concentration of A, resulting in an ordinary differential equation. If this differential equation is solved, it provides a prediction of the behavior of the concentration of A over time, which can then be compared to the data. This is referred to as an integral analysis. I will explain methods for differential and integral analysis of isothermal batch data in subsequent videos. So to review, while other reactor configurations are possible, the most common way to obtain kinetic data is to conduct a reaction in an isothermal batch reactor. This generally provides the concentration of a reactant or a product over time. The fundamental equation for analyzing an isothermal batch reactor, given the assumption of perfect mixing and constant volume for the reaction mixture, is that the rate of appearance of any species equals the time derivative of the concentration of that species. And there are two ways of analyzing the concentration data: a differential analysis, where we use the concentration data to estimate the value of the time derivative at various points in time, and an integral analysis, where we assume a relationship between the rate of reaction and the concentration of a species, solve the resulting differential equation, and compare the results to the concentration data. In the next video in this series, I will discuss how to analyze the data in differential analysis.